Good evening. My name is Mark Tessier-Levine, and I have the privilege of serving as president of the Rockefeller University. I want to thank everyone for joining us this evening for our inaugural Parents in Science Celebrating Science Benefit, Redux. Throughout its history, Rockefeller has been committed to educating the public about the latest biomedical breakthroughs. And 5 years ago, it strengthened these outreach efforts by creating the Parents in Science initiative. Parents in Science educates parents about science and provides a forum to learn about emerging discoveries and to engage in an intellectual exchange with scientists and with each other. Now, I think you know it's been a long journey to today's program. Tonight's benefit, as you know, was originally scheduled for November 7th, but was postponed due to the storm after Hurricane Sandy. After consulting with the Parents in Science Steering Committee, we decided to reschedule the event but redefine its format. Tonight, you will attend a reception and dinner buffet that may turn out to be even more festive than what was originally planned, as I'll explain after Dr. Lustig's talk. Now, since some of you have asked, I wanted to mention that everything purchased for the November event was reused either tonight, our programs are a perfect example of that, or it was donated to worthy charitable organizations. The food from the canceled benefit was given to the Lenox Hill Neighborhood House, which helps many elderly New Yorkers, homeless families, and others in need. And the floral arrangements were donated to patients at Memorial Sloan Kettering Cancer Center. I want to take this opportunity to thank Julia and David Koch for their extraordinary generosity in underwriting this event. This evening would not have been possible without them. David and Julia have done so much not only for cultural and educational institutions, but also to advance biomedical research. And we're fortunate that David is here with us this evening, and I'd like to thank you, David. I'd also like to thank our Parents in Science leadership, the outstanding group of co-chairs and committee members who took the reins for this new celebration. It's an extraordinary accomplishment to undertake planning an inaugural event of this scale not once but twice in just a few short months, and we're extremely grateful to you all. And I also want to recognize the Parents in Science Steering Committee, a core group of volunteers who've done a tremendous amount of work over the years to ensure the growth and success of Parents in Science. The names of these individuals are in your programs, and I'd like to take this opportunity to thank all of them as well. And finally, I'd like to thank all of you for your generous support. Proceeds from tonight's benefit will help launch a new Center for Research on Child and Adolescent Health to provide vital resources to the Rockefeller scientists who are transforming our understanding of human development and childhood diseases. So it gives me great pleasure to announce that we've raised a remarkable $1.1 million for Parents in Science through this benefit. Well done, and thank you. Now, tonight is also extraordinary because we have so many new friends with us. We have 150 guests who are visiting Rockefeller for the very first time. I'm delighted to welcome you to campus. Since so many of you are new to our campus, I'd like to say a few words about Rockefeller University, which is an exceptional place. Founded in 1901, the university is devoted to research and graduate education in the biomedical and related natural sciences. It's home to many of the world's leading investigators. The university has an unparalleled record of achievement, including more Nobel Prizes in medicine and chemistry than any other institution in the world, 24 to be exact. If Rockefeller University were a country, it would rank 4th in the world in Nobel Prizes after the United States, the UK, and Germany. Now, because so many guests are new to Rockefeller tonight, we thought it would be nice to share a short video about the university. So Todd, if we could have the video, please.
My daughter came down with a bad case of psoriasis. She was going to a dermatologist who was treating her, and she'd been through a number of treatments and nothing was working. And so finally I said to him, who is the leading psoriasis expert in New York City? And he said, it's Dr. Martin Carter at Rockefeller University. She wound up spending a month in the hospital the first time. And I remember I went over to pick her up, and I said to the nurse, "Where do I go to pay the bill?" The nurse said, there's no charge, it's a research hospital. And so I went back to my office and I got out my checkbook and I sent a check to Marty Carter for what I thought a month in the hospital would cost. And not surprisingly, about 2 weeks later, I got a call from the chairman of the board of Rockefeller who said he'd like to come over and see me. And that was the beginning of what now has been a 20-year relationship with the university. Rockefeller University was formed in 1901 by John D. Rockefeller Sr. And the reason it was formed was that we had reached the point in the state of medicine where you could diagnose what was wrong with people, but we had no ability to stop the disease that they had from killing them. Rockefeller had an advisor named Gates, and so Gates came up with the idea of bringing together the best and the brightest in one location to basically study how do we interact with disease and how do we stop disease.
My own laboratory studies a rare group of patients who, amazingly enough, have an immune response against their own cancers. We're able to discover something that people haven't seen before, which is human beings have a natural ability to get rid of cancer. Not only do the best scientists want to come here, but the best students, the best fellows, the best clinicians want to come work here. This is the #1 place in the country, possibly the world, to do this kind of research. So I'm privileged to have an absolutely spectacular group of people working with me in the laboratory now and hopefully in the future.
Rockefeller is important to what we're doing because it's one of the only places in the world that actually prizes risk-taking and has allowed us to do completely improbable scientific experiments that we just wouldn't be allowed to do at any other university. Mosquito disease transmission is an enormous problem in the developing world. Malaria kills 1 million people a year. Several hundred million people are sick and infected with the malaria parasite. To try to find out what that substance is that's either attracting or repelling mosquitoes, and that substance, if bottled, could be an incredibly important tool in preventing mosquito disease transmission.
Rockefeller is just an incredibly exciting place to be because of the strength of the basic sciences on the one hand and the commitment that's always existed here to taking that knowledge and translating it into medicines that can help patients.
We need to identify those with passion and with the intellectual capabilities to back up that passion to go into medicine and science.
Biomedical research is our only focus when we're here, as opposed to being at a large medical center where often your research competes with the time that's spent in clinical care. Rockefeller is second to none in providing that protected time. Obviously, I'm very thankful for the investment that Rockefeller has made in me. As part of the Clinical Scholars Program, I had 3 years of protected time. That gave me enough time to focus on my research, generate data. Now I'm an NIH-funded investigator, and that was not a small accomplishment, and I could do it thanks to the investment that Rockefeller made.
Rockefeller University is very unusual in that it is not divided up into departments reflecting different disciplines, because departments can form barriers between different sorts of research workers. What we have here, no barriers between the basic researchers and the clinical researchers.
Having no departments is critical. Every head of lab, tenured or not tenured, reports to the president of the university, period.
This is really the golden age of disease research, translational medicine, and drug discovery, and I think that medicine is going to be transformed profoundly in all of those different areas.
I think we have an outstanding opportunity here. We have a small institution with world-class people in it, and I think we need to continue to think aggressively about what else we can be doing at Rockefeller and how do we expand beyond our current scientific horizons.
My family have been involved in a number of enormously worthwhile philanthropies, but I believe that perhaps the most significant is the Rockefeller University and Rockefeller Hospital in that connection. I think going back even to grandfather and father, they would probably agree with that.
Somebody asked me, well, how can you keep talking about Rockefeller? You don't even work there. You're at Harvard. What's that all about? And I once said to a group there, well, I guess it sounds a little bit like Macy's complimenting Gimbels. And most people don't understand what I mean when I say that anymore. But I do feel that it is a place that sets a standard.
It is my single most important philanthropic association. It's an institution that has had a large impact on my family. It's been a very important place to me for a long time. I am totally honored to be chairman of the board, and it's a place that I think the world of, and want to do as much as I can to help.
Well, the scientific theme of tonight's benefit is most appropriate because Rockefeller has such a distinguished history in the science of obesity and nutrition. In fact, the modern field of obesity research began here with the groundbreaking investigations of Jules Hirsch. Jules is now in his 80s, but he continues his scientific work here at Rockefeller. The tradition continued with Rockefeller professor Jeffrey Friedman, who won the Lasker Award in 2010 for his discovery of the hormone leptin that helps to regulate appetite, energy expenditures, and body weight. A great breakthrough in understanding how the body controls food intake and body weight. It's now studied by scientists worldwide. And so it now gives me pleasure to introduce tonight's speaker, Dr. Robert Lustig. Dr. Lustig served as an associate physician at the Rockefeller University Hospital in the campus in the late 1980s and early 1990s. We're very pleased that he's returned to the campus to deliver this evening's presentation, especially after having been here in the fall as well to make that presentation. Now, Dr. Lustig is a professor of pediatrics at the University of California, San Francisco. His work exploring the role that excess sugar consumption plays in disease has received extensive media coverage, including a 60 Minutes feature last spring. His new book, Fat Chance: Beating the Odds Against Sugar, Processed Food, Obesity, and Disease, was released on December 27th. And to thank you all for joining us, you will be receiving a copy of his book in your gift bag when you depart tonight. Please see Dr. Lustig's biography in our programs for additional information, but in the interest of time, I'd like to proceed to his talk, and so please join me in welcoming Dr. Lustig to the platform.
Well, thank you very, very much, Mark. And I cannot tell you what an honor and what a privilege and what a pleasure it is to be able to come back and stand behind this podium when I spent so many hours in those seats where you are right now, listening to other professors that you saw on the video and many others as well, and also to be able to talk to some of the professors that taught me. For instance, Bruce McEwen, who I always considered my Dutch uncle, and I'm sure the reason I'm here tonight. Sarah Leibowitz is in the audience as well, who has done groundbreaking work on the regulation of food intake and has been a very important influence on the work that I'm going to show you as well. I want to thank my family as well for being here tonight, and many, many friends and honored guests. And I want to thank all of you for caring about this issue. And I'm going to tell you, you better care about this issue because this is the biggest issue in public health in the history of mankind. It dwarfs everything else. It dwarfs the Black Plague. It dwarfs tuberculosis. It dwarfs influenza. It dwarfs pollution. It dwarfs HIV. It dwarfs everything. And there are 35 million people dying every year from the diseases we're going to talk about tonight in developing countries, not developed countries. So much so that the UN Secretary General in 2011 declared that non-communicable disease, that is chronic metabolic disease, which we're going to talk about tonight, is now a bigger threat around the world than acute infectious diseases, including HIV. So when you think about that, and you think about the allocation of resources that has been made, and you think about what has happened to our healthcare system, you realize just how important this is from a public health standpoint. Worse yet, you're going to find out tonight there's no medicine for this. So understanding it, as Rufus Cole said, is what it's about, because that's the only way to deal with it. And I'm going to try to get you to understand it tonight. So with that, let me go ahead and get started. I have no disclosures. Promise, no food industry is, concern is putting me up to this. Certainly not. All right, here's the past. 2001, 12 years ago. 6 million kids are seriously overweight. Well, with all of the media attention, with all of the NIH research, with the discovery of leptin, which you will hear about, with Michelle Obama's vegetable gardens, we are now up to 20 million and counting. Here's the present. Currently, there are 30% more obese people walking the earth than there are undernourished people, and this is in the same country that has the undernourished people. I mean, this makes absolutely no sense. How can there be more obese people in Africa than undernourished people? But that's what's going on right now. 366 million diabetics walking the earth, 5% of the world's population, and they are chewing through all of the healthcare resources. There's no money for anything else. And here's the future. Experts predict 165 million Americans will be obese by 2030, 1/2 of the adult population. 100 million Americans will have diabetes by 2050, 1/3 of the American population. Again, no health care for you because Medicare will be broke by 2024. I will be 67 in 2024. No health care for me. And to be honest with you, no health care for you either. So this is a problem. And if you don't think it is, just go to Disney World. All right. So what are we talking about? This is an 11-inch statue unearthed in 1908. That carbon dates back to 22,000 BCE. It's known as the Venus von Willendorf. And what it shows us is that the ancients knew about obesity before they knew about McDonald's. Obesity is part of the human condition. If you go to the medical textbook, there are 60 different diagnoses that carry obesity as at least one of its markers. And none of them explain what has happened in the last 30 years. This is a phenomenon that has basically exploded in just the last 30 years. The question is, how did the world get so obese, and how did it do it so fast? So that's where this guy comes in, okay? Sort of one of our, guiding lights in medicine. So here's what you know. Obesity worsens, yes, in both prevalence and severity. It's increasing in all developed and developing countries, and it's increasing in all age groups, particularly in children. And recidivism is very high. The number of people who can lose weight and keep it off is vanishingly small, on the order of about 1%. Oh, you hear about them. You see pictures of them in the newspapers and the magazines. I lost 100 pounds, doing, this crazy diet or that, hydroxycut, this medicine, whatever. Bottom line, no one can do it. Because if anyone could do it, I wouldn't be standing here. The question is why? Well, the obvious explanation, the one you've been fed, gluttony and sloth. You're glutton and a sloth. You eat too much, exercise too little. Every doctor will tell you that, except me. Let's ask Darwin what's really going on. What would Darwin say? He would say this is evolutionary. He would say this is a mismatch between our environment that we have created for ourselves and our biochemistry, because our biochemistry was not adapted to our current environment. And when we understand what those mismatches are, we should be able to solve the problem. That's where we're going. All right, so to understand that, first we have to understand, why is obesity around in the first place? Why is it part of the medical condition? Well, there's a selective advantage. Energy storage for a rainy day. Okay? 7 years of famine, Joseph proclaimed. So those who could store energy better survived longer. This actually took place in Arizona twice. The Pima Indians have been selected for. In 1912, when a train trestle went out during a huge snowstorm and 90% of the Pima population was lost. The 10% who survived it were able to store energy the best. And then it happened again in 1938. Same thing happened. And so the Pimas have been selected for because they store energy the best. The problem is Now they are the sickest. And the question is, how is this selective advantage achieved? And so what we're going to talk about tonight are two phenomena. One called leptin resistance, and Dr. Tessier-Levine introduced the concept of leptin. I'm going to talk about it in a little greater detail. And also insulin resistance as well. And to understand what's going on, you have to understand these two. And we'll have to do just a little touch, a smidgen of science to get you there. Okay. So this is a very complex schematized pathway, but I want to have you focus on just one thing. This area over here in the brain, called the hypothalamus, controls energy balance. And these two hormones right over here, leptin and insulin, are what we're talking about tonight. Leptin, discovered right here at Rockefeller University in 1994 by Jeff Friedman and colleagues, is made by the adipose tissue and goes to your brain and tells your brain you have enough energy on board to engage in normal, expensive metabolic processes. You can burn energy at a normal rate and feel good doing it, and you don't have to eat so much because you have enough for a rainy day. Everybody got it? And then you have this other guy over here called insulin. And insulin's very interesting because it has two different functions. One, it tells the fat cell, hey, store fat. And it tells the brain, hey, I'm in the middle of metabolizing a meal. I don't need to eat so much. Let me finish what I've started. So it does two different things in two different parts of the body. It tells the fat cell, store, and it tells the brain, don't eat more. So that's kind of neat. And that's the nidus of what the obesity problem is, and I'll try to explain how. Okay? So in order to understand this, let's talk about a paradox. How many of you have children? Yeah, okay, good. It's parents and science. All right, so here's the question. If you give a 5-year-old kid a cookie, what happens? They're bouncing off walls. It's called the sugar high. Every parent knows this, right? Yes, I got a nod over here. They just go crazy, okay? And of course, all the teachers know this too. Now, how does this happen? Well, you eat the cookie, you lay down some more fat because insulin drove energy into the fat cell. The fat cell made leptin. The leptin goes to the hypothalamus. The hypothalamus says, hey, I don't need all that energy. I can burn it off. And so what it does is it increases a part of the nervous system called the sympathetic nervous system, which is also the fight or flight response, the reason you get scared and your heart beats faster, et cetera. And that goes to your muscles as increased sympathetic tone, which causes your muscles to twitch or fidget. So fidgeting is actually a protection against obesity, which is why all these kids fidget. And then, of course, that burns off energy. And so what you have here is a nice negative feedback pathway between the fat cell, the brain, and the sympathetic nervous system to keep you in relatively normal energy balance so that you don't go up or down too much. So far, so good. So here's the paradox. What if you give an obese 5-year-old kid a cookie instead? What happens? It's in the pantry looking for more cookies. Anybody ever see a sugar high in a fat kid? Doesn't exist. Can't exist. Reason? Because this kid's leptin isn't working. Because if his leptin was working, he wouldn't be obese. So he lays down more leptin, brain doesn't see it, because if the brain saw it, then he'd fidget it off. But no, he's looking for more. Everybody see the paradox? Something about obesity drives leptin resistance, and leptin resistance is obesity. And we're going to talk about that. Now, here is the most famous patient at Rockefeller University, right here. Right, Mark? This is Jeff Friedman's leptin-deficient mouse. It's actually Jackson Labs' leptin-deficient mouse before it was Jeff's. But anyway, this leptin discovered right here in 1994. And this animal can't make leptin because he has a gene defect. And so what happens is this animal eats everything in sight. But more importantly, this animal is the world's biggest couch potato. I don't know how many of you have ever worked with rats or mice, but they like to nest in their cages. They build up the bedding or the sawdust underneath, and they get into the corner, and, you know, these animals just stay where you put them. The only reason this animal ever gets off his hiney is if you put the food on the other side of the cage, then they'll waddle over there, eat the food, and stay there instead, okay? These animals have no energy to be able to engage in normal nesting behavior. They are too starved. Their brain never gets the signal that they're fat. Their brain sees only starvation because there's no signal from the fat cell to the brain to tell the brain that there's enough energy on board. Everybody understand? Okay. So how does this work? Well, here's a fat cell making leptin, and the leptin tells the hypothalamus, hey, I'm good. I've got enough. And so this phenomenon will drive one of these two processes over here. If leptin tells the hypothalamus what's going on, then you get this one over here called anorexigenesis. That is, hey, I'm not hungry, I don't need to eat so much, and I can burn energy at a normal rate. And so what it will do is it will tell the sympathetic nervous system, go ahead and burn off the energy, and it will also tell the vagus nerve, the energy storage nerve, the appetite nerve, shut down, I don't need to eat so much. And you'll notice the vagus nerve also innervates the pancreas, and that becomes important in a moment. But if leptin is low, that is, you're starving or you're undernourished, then your hypothalamus senses energy deficiency. And so then this guy over here goes into action, orexigenesis. I'm hungry, I need to eat, bring me food. And of course, I don't want to burn, I want to conserve, I want to store, and therefore, I'm not going to move. I'm going to sit on the couch, I'm going to watch videos or text or something else. But I'm certainly not going to engage in any form of exercise. Sound familiar? And so it is this balance between these two that drives energy storage versus expenditure. Now, there are 14 leptin deficient people in the world, 14. And they are all of consanguineous marriages, and they're all of Turkish or Pakistani ancestry, and they all live in the UK or Turkey. 14 of them. And if you take one of these patients, and you can see this patient was normal weight at birth, but started gaining weight immediately. By age 1, this kid is already massively obese because this kid will eat anything in sight. And the kid's 100 kilos, 220 pounds by age 9. And you start giving this kid shots of leptin every day, and look what happens. The kid loses weight on a dime. And not only does he lose weight, it's all fat mass. This kid is fixed because the gene defect, which didn't make the leptin, is now being made up by the fact that the kid's getting leptin from a bottle instead. Everybody got it? Hormone replacement therapy. It's what I do for a living as an endocrinologist. This is perfect. Okay? Problem is, only got 14 people like that. The rest of us are not leptin deficient. The rest of us are leptin resistant. We got plenty of leptin, look, plenty of it. And it correlates with how fat we are. So our leptin level is a marker for our body fat. But if our leptin worked at the level of our brain, we wouldn't be fat because we'd have burned it off and we wouldn't have eaten more. So this is the phenomenon that we're talking about tonight, leptin resistance. How does this occur? What is the phenomenon that allows this to occur, and how did it occur in 30 years? So this X over here marks the spot. This is the holy grail of obesity right here. If leptin is being blocked from being able to signal the hypothalamus, then orexigenesis takes over. I'm hungry and I'm going to play video games. And that's what we're seeing in today's youth, and to be honest with you, all over the world. The question is, what is that X? What's that question mark right there? All right, so now let's talk about the other hormone. What does insulin do? So remember I told you, insulin tells the fat cell store energy, and it tells the brain, hey, I'm in the middle of metabolizing a meal. Don't need to eat anymore. It's part of the satiety signal, acutely, but not always. This is the patient that started me in obesity now 18 years ago when I was an attending at St. Jude Children's Research Hospital in Memphis, Tennessee. This young man, this unfortunate young man, was perfectly normal weight at age 7. And then he developed this brain tumor right here, sitting in the middle of his hypothalamus. And he required surgery and radiation, and he became hormone deficient, and I had to replace all of his hormones. And he started gaining weight at the rate of 30 pounds a year, nonstop, ad nauseum, ad infinitum, and nothing this kid or his mother could do could stop the rolling on of the weight. This form of intractable obesity we call hypothalamic obesity. And if there's one thing that I'm sort of known for, it's figuring this out. What caused that? Well, basically, this brain tumor and the radiation killed that hypothalamus. So this hypothalamus now cannot see the leptin signal. So this kid can't ever feel normal. This kid can't ever feel like he's got enough energy on board. He's always tired, he's always miserable, and he's always hungry. And he keeps gaining weight like this. And the question is, what are you going to do about it? I was faced with a stable of these patients. What can we do about it? So the question is, how does this occur? So two different hypotheses over here. One, that damage to the hypothalamus leads to obesity because it tells your brain, hey, eat more. Or damage to the hypothalamus leads to obesity because it tells the vagus nerve to release more insulin. The more insulin drives more energy storage, which therefore drives the weight gain. Now, if this is the case, not much I can do about it because I can't fix a brain. I think Dr. Tessier-Levine can do that, but I can't do that. But if this is the case over here, it gives us a place where we could potentially intervene. Right here, between the vagus nerve and the beta cell of the pancreas. And we have a drug that blocks that insulin release at the level of the pancreas, and it's called octreotide, and I know how to use it because I'm an endocrinologist. And so what we did was we said, let's take these kids and let's give them this drug and see if it has any effect on their food intake, on their weight, and on their quality of life. So here's one patient, 220 pounds here, and here she is a year later, 172 pounds. And the apocryphal story about this patient was that after 1 week of therapy, kid hadn't lost any weight yet, 1 week, mother called me up on the phone and said, Dr. Lustig, I don't understand, something's going on here. I go, how do you mean? Mother says, well, we would go to Taco Bell, and she would eat 5 tacos and an enchilada, and she'd still be hungry. And now, we just went to Taco Bell, she ate 2 tacos, and she was full. And she just started vacuuming the house. I went, really? Wow. And in fact, we started seeing this in all of our patients, that they started exercising spontaneously. One kid became a competitive swimmer. 2 kids started lifting weights at home. 1 kid became the manager of his high school basketball team, running around collecting all the basketballs. I mean, these were kids who sat on the couch, ate Doritos, and slept because their brain couldn't get the leptin signal, and now they were burning energy voluntarily. Kind of neat. Well, here's that patient, the competitive swimmer. Here she is, BMI of 28 over here at age 10, and here she is 6 months later, BMI down to 24, and here she is in her swimming togs 2 years later after the study was over, and you can see that despite her best efforts to try to do something about her weight, her BMI had grown all the way up to 34.5 because the problem was still there and the drug had been stopped because the study was over, the insurance company wouldn't pay for it, and so basically she was left to her own devices, and here she is now trying desperately to do something about it and can't. We finally got the insurance company to foot the bill for the drug, we put her back on, and her BMI went back down to 27. That's Koch's postulates fulfilled. Not this Koch, but different Koch. And finally, here's that proband patient I told you about before. 364 pounds here, and here he is, the 326, first time he took a picture with his shirt off. And here's the pièce de résistance. This isn't even my patient. This is a lovely young 13-year-old girl in Hawaii, you can see. And 2 weeks after this picture was taken, she was in a car accident. And she stroked her hypothalamus. And here she is 1 year later, not able to control her weight because everything she eats gets stored. Because her insulin levels are so high, it's driving her energy storage nonstop. Well, I gave a talk at Kaiser Honolulu, and they invited her and her mother to come hear it because they were thinking about putting this kid on this drug as well. And here we are together, and here she is 2 years later at her high school graduation. Pretty neat, huh? So, here's how this works. Each of us is really 2 compartments. There's you, your heart, your liver, your lungs, your kidneys, your muscles, your lean body mass, which burns energy, and then there's your fat, which stores it. Now, the substrate for both compartments is glucose. Glucose feeds both of those. But glucose is never at saturation for both compartments at the same time. You can't eat that much, no one can. That means there's a competition going on for the glucose. Which compartment gets the glucose? Well, your insulin determines that. When your insulin's high, the glucose goes to your fat. Now, normally your fat would make leptin. The leptin would feed back on the hypothalamus and tell the brain, hey, I got enough, so it would reduce the food, therefore it would reduce the glucose, therefore the insulin would go down, and so here you have that same nice negative feedback pathway I showed you at the beginning. Except these kids have a CNS insult, they have a brain insult. And so their brain thinks they're starving, so their vagus nerve goes into overdrive to tell the pancreas, release more insulin, driving everything into their fat, so they keep gaining weight, gaining weight, gaining weight. They have nothing to burn, so therefore they feel lousy. So we block that. Now the glucose goes to them. Now they lose weight, eat less, feel better, reverse the metabolic process. Pretty neat. And so then we ask the question, okay, this is pretty great for these kids. What about garden variety adult obesity out on the street? So we did 2 studies, one a pilot, one a double-blind placebo-controlled trial, where we gave this same drug, octreotide, to overweight people without brain tumors. And here's an example. Christmas 1998, this lady's holding up food, I believe, and here she is 35 pounds later in her jogging togs because she wanted to show me that she actually liked to exercise. She wanted to exercise. So, what does this all mean? Well, when leptin tells the hypothalamus what's going on, all's right with the world. But clearly something gets in the way, and the question is, what's the thing that gets in the way? Well, it's the insulin. Insulin blocks leptin signaling. It also tells the fat cell to store. So you store and you don't burn all at the same time. So everybody thinks gluttony and sloth are 2 different problems. No, they're not. They're the same problem because the insulin interfered with that leptin signal at the level of the brain. The question is, what's that insulin doing and why is it high? So insulin is an endogenous, that is, you make it yourself, leptin antagonist. It blocks leptin signaling. Now, why would God do this to us? What's the selective advantage? And the answer is, there are 2 times in your life you actually have to gain weight. Puberty and pregnancy. And both of those are insulin-resistant states on purpose because you need to gain the weight. So your insulin goes up specifically to drive energy into fat for reproduction, and so that the brain knows that it's time to gain the weight, because if your brain was working right all the time and your leptin was working right all the time, you could never gain the weight. Species would die out. So this makes perfect Darwinian sense. Doesn't it make sense that the same hormone that promotes the energy storage would also work at the brain so that the energy could be stored? Makes perfect Darwinian sense. Problem is, we're only supposed to be able to do this twice in our lives. And we're doing it 24/7, 365. Why? Because we're all hyperinsulinemic now. Our insulin levels are 3 times higher than they were 30 years ago. If you do an oral glucose tolerance test today, you get a peak insulin response of anywhere from 100 to 150. You did that same test to our forebears 30, 40 years ago, you got a peak insulin of about 50. So we're all releasing more insulin than we used to. And the question is, how come? What happened? What changed in the last 30 years? And to answer that question, I'm not going to answer it for you. I'm going to let Will Smith answer it for you, okay? Because even Hollywood knows the answer to this question.
What? I guess I owe you some answers, Hoss.
Oh, what, you feeling chatty all of a sudden?
Sorry, I can't talk right now. I got some secret cases of my own I'm working on.
I hate to tear you away from your video game.
All right, I'm hanging up.
You know the most destructive force in the universe?
Sugar?
I didn't say it. But it is the most destructive force in the universe. Indeed it is. And I'm going to show you why. So this, some of you probably saw in the New York Times back in April of 2011. It's about our research at UCSF. This was a comment that we had in Nature last year called The Toxic Truth About Sugar, which goes into the reasons and the whys and wherefores of why this has occurred and what we need to do about it. So what are we talking about when we talk about sugar? Well, there are two kinds of sugar that we're talking about. We're talking about sucrose, or we're talking about high fructose corn syrup. So high fructose corn syrup, of course, is the most demonized additive known to man. Everybody knows it's a problem, but they don't know why. They don't know why it's a problem. Well, I'm going to show you why it's a problem. It is one glucose, right here, 6-membered ring, and one fructose, 5-membered ring. Now, glucose is not very interesting. You see people going around chugging Karo syrup, molasses, But this stuff over here, now this is, this is the bomb. This is what we care about. This is what we go out and seek. And in fact, this is what we are addicted to, and I'll show you that data as well. But you can see one glucose, one fructose. But you notice sucrose, table sugar, cane sugar, beet sugar. One glucose, one fructose. O-glycosidic linkage linking the two, so what? The intestine has an enzyme that cleaves this in about a nanosecond. When you absorb it, it's the same thing. And all of the studies comparing high fructose corn syrup to sucrose show absolutely no difference, no metabolic difference. High fructose corn syrup and sucrose are equivalent, equivalently bad, equivalently poisonous, equivalently toxic. And I'll show you how. Okay? Everybody got that? Plus, high fructose corn syrup is only available in the United States, Canada, Japan, and very limited exposure in parts of Europe. Yet the entire world has this problem, I already told you, because they have sugar. Here's what's happened in America in terms of our fructose consumption. Our forebears, about 100 years ago, getting fruits and vegetables out of the ground and the occasional honey, consumed on average about 15 grams of fructose per day. Double that for sugar, because glucose and fructose weigh the same. So it'd be about an ounce of sugar a day. Prior to World War II, with the nascent candy and soft drink industries, we got up to about 20 grams a day. By 1977, just before the glut of high fructose corn syrup hit our shores, we were up to 37 grams a day. That was 8% of our total caloric intake. By 1994, we were up to 55 grams. That was 10% of our total caloric intake. And currently, adolescents average 75 grams a day, or 12% of total caloric intake. And 25% of adolescents consume 100 grams a day. So double that for sugar. That's 200 grams of sugar per day, multiplied by 4.1 calories per gram. That's 840 calories in sugar alone. So for a normal caloric allotment of 2,000 calories a day, that's 40% of calories of sugar. That's what our kids are consuming today. The question is that okay? Can you handle it? Can you handle that much? Can your liver handle it? Could this potentially have downstream metabolic consequences that are a problem? That's the question. And here's the denouement. Of the 600,000 food items in the American food supply currently available, 80% of them have added sugar by the food industry specifically for its purposes. Not because we asked for it, but they gave it to us. So, if you think your food supply is your food supply, think again. It's their food supply, because they have co-opted your choice. And the question is that okay? You allowed it with your tacit approval. They did it. And they did it for two reasons. One, because they mastered the two main philosophies of marketing. One, we give the public what it wants. And two, if you build it, they will come. And they've mastered both. And I'm going to show you what that has, what problems that has wreaked upon us. But you know, this isn't just America that's doing this. This is the whole world that's doing this. I've already told you, 35 million people a year dying of chronic metabolic disease. So this is worldwide per capita sugar supply, and here we are, of course, the most overwhelmed, okay, at 629 calories a day. But you'll notice, the American Heart Association says, reduce your total sugar consumption to between 150 to 200 calories per day in sugar, right here. How much of the world is over that threshold? And look what happened to world sugar consumption during that period of time. So 1960 to 2006, tripled. Per capita consumption, Brazil is now a sugar consumer. It used to just be a sugar exporter because its populace couldn't afford the sugar it made. But now Brazil has the highest increase in rate of prevalence of type 2 diabetes in the world. Not the highest prevalence, but the highest increase in rate, the highest acceleration of prevalence. And they are the biggest consumers. Who has the highest prevalence of type 2 diabetes? Saudi Arabia and Malaysia. Saudi Arabia and Malaysia, how do they do this? No alcohol. But they got soft drinks like they're going out of style. Because it's hot, and the water supply is a question mark, and no alcohol. Right? This is their reward. This is their reward. This is their addiction. And they are consuming sugar like nobody's business. I was just in Kuala Lumpur, and let me tell you, it's really a problem when everyone there enters a room 10 minutes before their feet do. That's how bad it is. The point of this is that you have been told time and time again by the food industry, by medical professionals, and by the federal government, eat less, exercise more, because a calorie is a calorie. If you burn less than you eat, you'll lose weight. That's what they've told you. Ain't true. And the reason it ain't true is because a calorie is not a calorie. And if you take nothing away from tonight, other than that notion, I will have done my job. A calorie is not a calorie. How do we know that? I'll give you 4 different ways. Number 1, almonds. You eat 160 calories in almonds. How many of those do you absorb? 130. What happened to the other 30? The fiber in the almonds delivered more nutrient down the intestine, preventing its absorption early so that the bacteria in your intestine chewed it up instead of you getting it. And that's good, because that means you absorbed less than you ate, because a calorie is not a calorie. Protein. It costs twice as much energy to metabolize protein for energy than it does to metabolize carbohydrate for energy. That's an energy deficit, because a calorie is not a calorie. Number 3, fats. Over here we have omega-3s, which are fantastic, heart healthy, save your life. Over here we got trans fats, right? The devil incarnate, poison, it'll kill you. Okay? They're both 9 calories per gram. And one will save your life and the other will kill you. Why? Because a calorie is not a calorie. And finally, because fructose is not glucose. What is different about that 5-membered ring? Everything. Fructose is 7 times more likely than glucose to form advanced glycation end products. That is the Browning reaction. It's called the Maillard reaction. And also discovered here at Rockefeller University in terms of hemoglobin A1C by Tony Cerami back in the early 80s, and we worked with him on that. Fructose does not suppress the hunger hormone ghrelin, the hormone that basically goes to your brain and tells you you're hungry. So if it doesn't suppress it, you eat more. Fructose does not stimulate insulin, and therefore you don't generate a leptin response. Well, if you get a leptin response, you get the sugar high. If you don't get the leptin response, you don't. So guess what? You don't burn as much energy. And finally, liver fructose metabolism is completely different from that of glucose. Completely. And I'm going to show you that chronic fructose exposure alone promotes all of those diseases, those chronic metabolic diseases, type 2 diabetes, dyslipidemia, hypertension, cardiovascular disease, and likely cancer and dementia as well. Now, if you want to see all the basic science and all the biochemical pathways, there's a YouTube video that has 3.2 million hits on it called Sugar the Bitter Truth, where we go into this in exhaustive detail. I am not going to bore you, and I don't have the time for that. But I'm just going to show you one thing. When glucose enters the liver, what happens to it? This is what happens to it. It goes to this guy over here called glycogen. Glycogen is liver starch. Glycogen is what your liver wants to do with energy. That's why marathoners pasta load before a marathon, is to try to build up their glycogen stores so they have more glycogen in their liver. So this is a good thing to do. This is a good thing to build out of it, okay? But that's what glucose does. Let's talk about a different carbohydrate. My favorite, maybe yours too. Let's talk about alcohol. Okay, there's carbon, hydrogen, oxygen. But you know what? We know ethanol is a toxin. It's two toxins in one. You wrap your Lamborghini around a tree, you fry your liver. Acute alcohol toxicity, chronic alcohol toxicity. We keep it out of the hands of children because we know it's a toxin. But it's a nutrient, right? Burns for calories. Here's acute alcohol exposure over here. Read through it, you all went to college. Over here, acute fructose exposure, nothing, because the brain does not metabolize fructose. It does metabolize alcohol. So let's now consume alcohol instead of glucose. See glycogen? Bypasses glycogen, no glycogen. What does it do? It goes all the way down here to the mitochondria, the little energy-burning factories inside each cell, and it makes fat over here. Lipid droplet, alcoholic fatty liver disease, and high triglycerides, which then can promote obesity and also promote atherosclerosis. Not so good. And now let's do fructose. So let's consume fructose instead of alcohol or glucose. See glycogen anywhere? Bypasses glycogen, same as alcohol, down to the mitochondria. So what do? You get the fatty liver, you get the triglyceride, you get insulin resistance over here, you get hypertension, you get muscle insulin resistance. That can be driven into the fat cell. Now you've got obesity, and worse yet, we know that because of that insulin resistance, we block leptin. So now what we have is a positive feedback effect between sugar, the liver, the pancreas, and the brain to promote continued consumption and chronic metabolic disease. Not good. So, what's the difference? Can of Coke, can of beer. What's the difference? 150 calories both. 75 glucose, 75 fructose over here for the 150. 90 alcohol, 60 maltose, that's glucose for the beer. The GI tract metabolizes 10% of the alcohol, so the number of calories reaching the liver are virtually the same. And so the same strain on your liver occurs with either one. So in America, we have this thing called beer belly. Welcome to soda belly. That's what we've got. And that's what our kids suffer from, soda belly. Because it's the same thing. It's the same phenomenon because it's metabolized the same way. So fructose induces insulin resistance at the level of the liver. And when that happens, the pancreas has to make extra insulin to make the liver do its job. That gets in the way of the leptin, and so now you've got leptin resistance, and so you keep eating. That's the reason for the continued consumption. All right? What would Darwin say? Would he say that this made any sense? And the answer is, yeah, it does. It makes perfect sense. Because there's a phenomenon called seasonal insulin resistance, and we see it in animals. The fact is, fructose used to be hard to come by. It was really only available 1 month a year. It was called harvest time. Harvest time. And so the fruit would drop from the tree, and we would gorge on the stuff because, hey, it was good, and we would lay down more fat. And then what followed harvest time? 4 months of winter. And we would go into caves and hibernate or otherwise. And the bottom line was, we needed that extra fat laid down in advance of winter specifically to be able to survive it. So it actually makes perfect sense that fructose would induce insulin resistance. It's part of survival. The problem is, if leptin worked all the time, you couldn't store the energy, so you have to have that selective advantage. But now fructose is available globally 24/7, 365, and consumed in unlimited amounts, for instance, the 2-liter bottle, and unopposed by fiber, like orange juice. So, orange juice, insulin resistance, obesity, chronic metabolic disease. And how do we know this is true? Because this is data from orangutans in Papua New Guinea. So here is their masting fruit orgy over here, where the availability of fruit goes haywire. And here's what you can see, that when that happens, virtually everything they eat is fruit and nothing else. And you can see that their calories go right through the roof while that's happening. And notice their ketones disappear, which is a sign of the fact that their insulin is high, because insulin blocks ketone formation. So you can see that this is Darwinian, this is evolutionary, this is what we're supposed to do. We're just only supposed to do it 1 month a year. And now we do it every day. Okay. Now remember we talked about this whole question about sugar making you eat more. So the question now is sugar addictive? You know, the whole public, seems to know this. I don't know why it's so hard for the scientists to get behind this. But they will tell you, we don't really know that, this, that, the other thing. Okay, bottom line, we're going to show you. So we have 5 sets of taste buds, 5 different tastes on the tongue. And sugar hides the other 4. It hides salty, like Chex Mix or honey roasted peanuts. It hides sour, like German wines or lemonade, right? Because, citric acid is sour. It hides umami, that taste like roast beef or sweet and sour pork. That's half soy sauce. You wouldn't eat that. Except the sugar, you can't even tell it's there. And it hides bitter, like milk chocolate, right? Because caffeine's bitter. Bottom line is you can make dog poop taste good with enough sugar. And the food industry does, and they know it. And that's how they get you to eat more. So does this make Darwinian sense? And the answer is, yeah, that's Darwinian too. Because there are no foods anywhere on the planet that are natural, that are sweet and both acutely poisonous. Think about that. Nothing on the planet that is both sweet and acutely poisonous. You all have children, you said so. How many times do you have to introduce a savory food to an infant before they'll accept it? 13. Science says 13 on average. How many times do you have to introduce a sweet food before they'll accept it? Just once. Just once. It's ingrained in our DNA. Okay? If it's sweet, it's safe to eat. And that's true acutely. But now we know chronically ain't so. Our sugar craving is very Darwinian. And here's a perfect proof of concept. Anybody ever heard of this stuff? Sweeties? Anybody know what it is? Your kids get circumcised? They got it, okay? Because this is a super concentrated sucrose solution that you dip the pacifier in, you stick it in the baby's mouth, and you do the circumcision. And it promotes an opioid response in the reward center of the brain. That's its analgesia. Okay? Even in neonates. So we love this stuff. This is addictive when you do it nonstop. Okay, now, Darwin diet, now we're up to disease. I love this part. Here are the 10 most obese states in the nation. No surprise. Here are the 10 laziest states in the nation. What's going on over there in Nevada? Guess you can only burn so much energy going like this. Now it's like this, right? Here are the 10 most unhappy states in the nation. Here's the adult diabetes rate. Here's the adult heart disease rate. And finally, soda per capita consumption. What do you see? What do you see? Virtual overlap, yes? Now, this is correlation, not causation. Okay? And I have been accused of pandering to the audience on this, okay? Because maybe unhappy fat diabetics consume soda. Or is it that soda makes you unhappy, fat, and diabetic, which you don't know directionality. You can't tell. This is correlation. Doesn't establish directionality, does not establish causation. But I wouldn't even show this to you if I didn't have causation. So, this is a paper that will appear in exactly 2 weeks from today in a very reputable journal called PLOS ONE, Public Library of Science 1. And I will tell you right now, this is the best work I've ever done. And I am very excited about it, and there will be a press release, and you will hear about it. Okay, and you're getting first dibs. What we did was we took 3 databases that exist on the web, and we linked them together. The Food and Agriculture Organization Statistics Database, which has food supply, country by country, and all the way through the decade 2000 to 2010. And we looked at total calories, fruits excluding wine, oils, roots, tubers, pulses, nuts, and vegetables as the fiber-containing foods, meat, cereals, and sugar crops, and sweeteners. Okay? Pretty much the whole gamut of the diet. We didn't look at micronutrients, which is important, but we didn't have that. We linked that to the International Diabetes Federation database for diabetes prevalence country by country throughout the entire decade. And then we linked that to the World Bank World Development Indicators database to look at purchasing power parity and to control for urbanization, aging, obesity, important obesity, physical activity, and GDP. And we asked the question, what about the world's food supply predicts diabetes prevalence over this past decade? Because we know diabetes has just gone through the roof. What in the food predicts the change? So we had 204 countries total, but we had complete data for 154. The 50 that were not included were not different. We tested that statistically. And we did a whole lot of fancy analyses. And I'm just going to point out one. This one over here, it's called the Granger causality test. How do you do that? Well, number one, we don't have the photograph. This isn't one snapshot in time. We have the movie, because we have the whole decade. And we can determine whether the change in any given foodstuff precedes the diabetes rate increase or follows it instead. In addition, we can determine whether those countries who increased their consumption of any given foodstuff had an increase in prevalence, and those who decreased consumption of a foodstuff had a decreased prevalence. So we have bidirectionality. So this is the Granger causality test, and it's the best you can do in terms of being able to figure out causation. Okay? And we controlled for all these things: GDP, obesity, urbanization, aging, and physical activity. And here's the data. So during this decade, diabetes prevalence rose from 5.5 to 7%. And here's the effect size right over here. And you'll notice that for every 100 calories in sugar, diabetes prevalence increased by close to 1%. And here's the adjusted association, adjusting for all of those things, of sugar versus diabetes prevalence, having nothing to do with obesity because we controlled for it. So here's the take-home message for all of you. Only sugar correlated with the changes in diabetes prevalence. Total calories was irrelevant. Irrelevant. For every 150 total calories you ingest extra, your diabetes prevalence increases by 0.1%. But if those 150 calories happen to be a can of soda instead, then your diabetes and prevalence increased 11-fold by 1.1%. And we don't consume 150 calories in added sugar in America. We consume 450 calories per day in added sugar. So that's 3.3% to you. You've increased your diabetes prevalence by 3.3% if you consume sugar on an average basis in America. And those countries whose sugar consumption declined showed decreased diabetes prevalence. And when you do the math, we show that 25% of the world's diabetes is due to sugar and sugar alone. Alone. You want to do something about chronic metabolic disease? Here it is. This is it. Do something about this. Now, there are limitations to this kind of analysis. It's called an ecological analysis. It's not raw data. And certainly there are issues about what is known as the ecological fallacy. Could it be that the patients who didn't consume the sugar were the ones who actually got the diabetes? You can't tell from percentages. That's why this is econometric. But we have other controls built in to make sure of that. It's food supply, not food consumption, but wastage is about normal, about 29%, even in the United States, and we looked at that. It's only one decade in time, but it's the whole decade. It's not a complete dietary analysis. Like I said, micronutrients were not included. Different techniques to screen for diabetes in different countries. Different diagnostic criteria for diabetes in different countries, but usually the same criteria for any given country. And some countries use self-reported data, and a lot of diabetics go undiagnosed, so probably the data is actually worse than we even said. And it includes both type 1 and type 2 diabetes, but type 1 hasn't changed that much. Type 2 is the thing that's gone through the roof, so we don't think it's being driven by the type 1s. So here's what we think is going on in very simple terms. Here's the fructose coming into the liver. And the fructose will get metabolized by the mitochondria and will throw off these little hydrogen peroxides called reactive oxygen species. This is the Browning reaction right here. In addition, the fructose will bind to proteins and throw off oxygen species. In addition, as you lay down visceral fat, the inflammatory cytokines, like TNF-alpha and IL-6, will bind to its receptor on the liver and generate more reactive oxygen species. So you've got this whole pool of these little hydrogen peroxides that want to do damage. Now, you have an organelle in your liver called the peroxisome, and that's where those little hydrogen peroxides go to die, if you can handle them, if you got enough antioxidants to handle them. In the liver, it's called glutathione. And if you don't, then they come up here to the endoplasmic reticulum, which is where insulin gets folded. And if you don't fold the insulin right, you get something called the unfolded protein response, which can kill the cell or at least cause diabetes. And there is no drug target for this. There's no way to clear those. There's no way to get rid of them. The only thing you can do is reduce the availability, that's called diet, reduce the flux to the liver so it doesn't happen all at once, that's called fiber, or burn them off before they have a chance to do damage, and that's called exercise. Diet and exercise again? But not exactly, because we're not talking about eat less. Eat less what? No one can eat less. But could you eat less sugar? Damn right. Could you eat more fiber? Absolutely. So what do you call a low sugar, high fiber diet? Anybody know what it's called? It's called real food. Got it? This is a processed food phenomenon. By taking the fiber out for shelf life, because you can't freeze fiber, and by adding the sugar so that we get to eat more, the food industry has driven this pandemic of chronic metabolic disease. And we can't fix it until the sugar leaves and the fiber comes back. It's called real food. And finally, to end the talk, dollars. So here's where our food dollars have gone in the last 30 years. Meat's down a little because of the low-fat directive of the 1970s and 80s. Fruits and vegetables about the same. Grains and baked goods about the same, a little bit higher. Dairy products down a little because everybody thinks they're lactose intolerant. And take a look, processed food and sweets doubled in the last 30 years. There it is. And who's making the money off that? So, this is stock prices for McDonald's, Coke, and Pepsi against the S&P 500. Now, this is not profitability of the companies. This is profitability of the stockholders, right? But you'll notice, they're doing very well. Here's the economic downturn of 2008 right over here. And you'll notice, they're all doing very well, thank you. And here's Hormel, Archer Daniels Midland, General Mills, Kraft, Conagra, Procter & Gamble, all doing better than the S&P. Want to make money? Invest in a food company. Indeed. And worse yet, the food industry can't do anything about it and doesn't want to do anything about it. Anybody know who Indra Nooyi is? She's the CEO of Pepsi, right? And they make more things than just Pepsi-Cola. They make all sorts of things. They make snacks of various sorts, right? They have Frito-Lay, et cetera. So she is from India. She's from Madras, India, and she sees what's going on in the Indian subcontinent. And the diabetes epidemic there is a disaster. And it was written up in the New York Times about 2 years ago. Big 4-day article, string of articles about what's going on in India. And she wants to fix it. And so they've introduced new products, and they've put more money into their good-for-you category as opposed to the fun-for-you category. And guess what happened? Pepsi-Cola went to number 3 after Diet Coke. And so what do you think happened after that? The stockholders and the board of directors called for her head because they're on a 3-month cycle, because it's all about the money. So she would like to do something and can't. This is what we've got. As long as it's about money, we can't fix this unless you fix this. Societal intervention requires negative impact on society we call externalities. So if you smoke or drink or take drugs, it's bad for me. So like secondhand smoke is bad for me. Car accidents are bad for me. Declining house prices, because the crack den next door to my house is bad for me. And, because you smoke, drink, or take drugs, you're out, in terms of absenteeism, that's bad for me too, because I got to do your job too. So how does your obesity affect me? That's the question. $274 million for jet fuel. Nah, that's not going to do it. Discomfort on the subway. You've all had that. Nah. Sinking of boats due to the weight. 2003, Lake George, ferry, coded for 17 people of 140 pounds, and it was 24 people of 195 pounds, and the ferry sank. You're not going to do it either. So what will do it? Here's what will do it. $65 billion reduction in work productivity, 50% increase in absenteeism, 50% increase in health insurance premiums that you all pay every single day, $150 billion in wasted health care resources. If you have an employee, you have to pay $2,750 extra for the premiums for their insurance because of obesity that your employee doesn't even have. Obesity is a threat to national security because 27% of recruits can't pass the physical because they're fat. And finally, most importantly, the government pays twice. They pay for the corn subsidy, and then they pay for the ER visits. And that's what's breaking the bank, and that's why Medicare will be broke by 2024. We need to be able to recoup the money somewhere, and we can't. So let me summarize for you. This is the Darwinian explanation, not gluttony and sloth. Here's what I've told you. Obesity means leptin resistance or brain starvation. The starvation response is what causes recidivism because your brain can't see the leptin. Energy expenditure and quality of life are the same thing. How fast you burn energy is how good you feel. And when you can't see your leptin, you feel lousy. Defects in insulin signaling promote leptin resistance. Insulin is an endogenous leptin antagonist getting in the way so your brain thinks it's starving. Fructose, because of the effects it has on the liver, induces that insulin resistance, driving those chronic metabolic diseases and wasting all of those healthcare dollars. And fructose is addictive and drives excess food consumption. So it's a vicious cycle of toxicity and consumption. Our food environment is fructosified, and in order to fix this, we have to get the insulin down, and the only way is to get rid of the sugar. Problem is, the food industry has no impetus to change its practices whatsoever. So how are we going to fix it? The legislative and executive branches of government are co-opted. Co-opted because 6% of our exports are food. What happened when that one downer cow went from Canada to Washington State in 2006? That was the end of meat sales to Britain and South Korea for 2 years. The government can't act on this. Plus, Congress is bought off by the food industry through various political action committees, which I can tell you about later if you like. So what do we have left? We have legal and we have public media. So public media, well, 60 Minutes. I was on CBS this morning. We're going to have a press conference about our paper 2 weeks from now. And what about legal? This is how tobacco worked. It was only a legal challenge that brought big tobacco to the table. Same thing's going to happen here. And that is why right now I am doing the first year of law school as a master's to learn the tobacco playbook at University of California, Hastings College of the Law. And we're going to bring it to them. So for further reading, I have whole bunches of academic tomes for you, and more tomes for you, and more tomes for you. And finally, you'll all be armed with something that is a little bit more palatable and storable on your way home tonight. And with that, I want to thank Mark and Bruce and all of you for your attention.
We'll take some questions.
Absolutely.
Well, thank you, Rob, for a most provocative talk. I know that there are going to be plenty of questions from the audience. Maybe I can start with, I'll use the chairman's prerogative and ask you two. First, if your longitudinal study says that sugar accounts for 25% of diabetes, what accounts for the other 75%?
Really good question. There are going to be genetic influences there. Not all of that is type 2. There are other things factored in there. There are a whole bunch of diabetes that aren't even type 2 or type 1. There's mitochondrial diabetes, MODY, et cetera. They all figure in to a certain percentage. But probably there are other factors in the environment that are also problematic. For instance, at Harvard School of Public Health, Walt Willett's group thinks that processed red meat is an extremely important factor that might explain diabetes. If you look at unprocessed red meat, 100 grams extra per day increases your odds-risk ratio by only 12%, but processed red meat, like bacon, 50 grams increases your odds-risk ratio by 51%. It's what came out. So there may be other factors that are involved. I also think micronutrients are extremely important in this, and we weren't able to assess that in this evaluation. But for the most part, type 2 diabetes is an environmental phenomenon. This is an environmental insult, not something that's really genetically driven.
Maybe I can ask also, in terms of establishing the impact of sugar on diabetes and fructose in particular, the longitudinal study you described seem to, they all point in that direction as you've described it. Certainly. I guess it'll be published in 2 weeks.
Right.
Are there clinical, typically complementing that, we like to have, randomized clinical data to do that. Are there such data, or are you planning experiments like that?
Well, we are doing a study right now at UCSF, which is a fructose withdrawal study in children. So we're taking children who have metabolic syndrome, obesity, plus at least one comorbidity, and we are studying them at baseline with various parameters, and then we're basically catering their meals for 10 days. Isocaloric, in other words, no change in calories, so no change in weight, but sugar-free for 10 days, like Domino's, we deliver. And the question is not, will they lose weight? They won't. The question is, will their metabolism, will their metabolic comorbidities improve in those 10 days? Now, we're in the middle of that study. We've done about half the patients that we need to. I am blinded, so I do not have the results of that. We will probably have those results in about 2 years. So we're trying to answer that question.
Thank you. Heard you first on Alec Baldwin. Here's the Thing, that was great. Played it for my whole family after that. Can you talk about diet soda?
Yes, everybody wants to know about diet sweeteners and diet soda. A paper just got released 3 days ago that said diet soda was a cause of obesity as well. And actually, there are a lot of studies that actually intimate that. I can't tell you the answer to diet soda or whether diet sodas are good or bad or otherwise, and here's why. There's something called pharmacokinetics, and there's something called pharmacodynamics. They're not the same. Pharmacokinetics is what your body does to a drug. Pharmacodynamics is what a drug does to your body. Not the same. We have all the pharmacokinetics for all the diet sweeteners because the FDA demands it. They won't put a sweetener on the market without all those pharmacokinetics because those pharmacokinetics tell you whether something is acutely poisonous. But we have none of the pharmacodynamics because the FDA does not demand it. So all of the pharmacodynamic studies would be 6-month or 12-month studies, long-term studies. So do any of these diet sweeteners affect your leptin or your ghrelin or your long-term energy intake or your metabolism rate or any of those things? We don't know. We don't know what any of these diet sweeteners do. Does the body compensate for the lack of them? We don't know. We don't know any of those things, because the FDA doesn't ask for it. And the food industry says, well, we can't sell any more if we did them, so they don't do it. And the NIH says, well, that's the food industry's job, so we're not going to pay for it. So we have a dearth of information that basically means I can't tell you the answer. I am about the science. I only talk science. And to do anything else would be pure conjecture. So I can't answer your question. And obviously, inquiring minds want to know. I want to know. And I can't tell you. And it sucks. Okay?
A question?
Thank you. So can you just, I'm a little confused then about the impact of sugar from fruit on a child's diet or an adult's diet.
Sure. Everybody wants, fruit is fine. Fruit is fine. Why? Because fruit has fiber. If you did a little graph of fructose content versus fiber content, it would be almost a virtual straight line, and every fruit would be on that line, except for one, grapes. Grapes are just little bags of sugar, okay? But everything else is on that line, okay? And I'll prove it to you. Sugar cane, okay? The foodstuff that has the highest sugar content of anything on the planet. It's a stick. You can't even eat the damn thing, right? You can't even chew it. It's so fibrous. Okay? So the fructose comes with the fiber. So when you consume fruit, you're consuming the requisite amount of fiber to delay the absorption from the gut into the bloodstream, and that gives your liver a chance to catch up so that you can metabolize it before you turn it to liver fat. So fruit is okay. Fruit juice is not. Oh, and by the way, smoothies are not either.
It seems to me that real food is what you've stressed.
Absolutely.
And why are there no major studies of really the nutritional value of wild strawberries versus processed strawberries and all of those different things? Because we had that data. I want to tell you something. I think that that would be a revelation to everybody and change America.
Yeah, and who's going to pay for it? That's the problem. Who's going to pay for it? The food industry should pay for it, right? Except they don't. Right? Their only job is to get it on the market. All they have to show is safe. That's all they have to show. And that's not good enough. But that's the way the FDA works.
What's the story with the other simple carbohydrates like rice and potatoes and bread and those?
Sure. So there's brown food and there's white food. Brown food is fiber-containing food. When wheat comes out of the ground, what color is it? Brown. Okay, when you turn it into bread, what color is it? Where'd the brown go? Got milled off at the mill, right? That was the fiber. That was the bran. So when you consume a whole grain and the starch is on the inside and the fiber's on the outside, you consume the whole thing, the enzymes in your intestine, the proteins that chew up your food, okay, have to strip that stuff off before the stuff comes out. That delays its absorption. That means that your liver doesn't get it all at once. And it means that it's more likely that more of it will go down the intestine and get chewed up by the bacteria, like I mentioned. Remember, you've got 100 trillion bacteria in your intestine. You only have 10 trillion cells in your body. Okay? Your bacteria outnumber you 10 to 1. So what you really ought to be thinking of yourself as, okay, is just a bacterial delivery device. Okay? Because they are, and they got to eat something. Okay? They got to eat something. What do they eat? They eat what you eat. Okay, the only question is, how much do you absorb before how much do they get? And fiber is the thing that gets them more. So brown food, like beans, lentils, nuts, other legumes, brown rice, etc., have the fiber. Yes?
Glucose is good and fructose is bad.
Right, okay, so glucose is not perfect. Right. Right. Right, so no, refined carbohydrate, flour, okay, starch, bread, rice, pasta, potatoes, white food, is glucose. It's glucose. Now, glucose without fiber will drive an insulin response. So you will release more insulin, and so that will store more fat. So refined carbohydrate does drive weight gain. And that's one of the reasons why the low-carb diet or the glycemic index diet or any of the, or the South Beach diet or any of the diets that you'd like to, talk about, will help with weight gain because it's keeping the insulin down. That's true. But I'm not talking about obesity. I'm talking about chronic metabolic disease. And refined carbohydrate can drive weight gain, but it does not drive that insulin resistance that we talked about. That's the key, and that's what sugar does exclusively. Difference. But thank you for pointing that out. I didn't make that point.
Question at the back there.
Hi, are glutamine and green coffee bean extract vitamins as good as people say for not absorbing sugar?
Hell if I know. I truly don't know the answer. I mean, there's a lot of stuff out there in terms of, nutritional mumbo jumbo, and there's very little science to support almost any of it. In the book, there's a chapter called Micronutrients, Home Run or Hyperbole. And I take all of these things apart, and when you actually look at the data, It's not very good. So I can't answer your question because I don't know the science on that.
We'll take one last question up there.
I'm just curious about, since with the rise of antibiotics, whether there might be any correlation with, you know, the sort of the change in the composition of the stomach flora and the effects that you were talking about.
There have been about 3 studies that have looked at that question. In fact, one just in Pediatrics about 2 months ago that brought that question up, that early antibiotic usage, especially in young infants for like ear infections, might change the flora and might actually contribute to obesity as well. And it's very tantalizing and very possible because there's a plausible mechanism. But these are, again, remember, correlative studies. You know, it's very hard to do causative studies because you can't give kids antibiotics unless they're sick. So we're going to probably not have the studies we need to answer that question specifically, but it is a big issue, and at NYU, Martin Blaser has written on this in Science magazine about this exact issue, about antibiotic use and possible its relation to obesity. It's certainly a possible confounder.
So before we close with the Q&A, I have an important announcement and a question. The announcement, I know it'll quell some anxiety in the audience. There will be dessert tonight. Not only that, but it will be cake, cheesecake and chocolate cake. And I believe, Rob, that your wife had a role
Yes.
in this evening's dessert.
Yeah, very important, very important.
Can you explain further?
Yes. So my wife is Norwegian, okay? And baking is therapy. Okay? I cannot stop her from baking. Okay? When she's mad at me, she bakes. Okay? She's doing it right now, I guarantee it. But she has experimented with all of this, and she has found that she can take any recipe in any cookbook and reduce the sugar in any dessert by 1/3, and it will actually come out better. It will taste better, it will still rise, everything will happen, all of the biochemical reactions in the baking process will still occur, and it will taste better. You can taste the chocolate, you can taste the oatmeal, you can taste the nuts. It actually tastes better. So that's your little extra added something for tonight.
That's right. Thank you, Rob.